Today we're going to take a look at lesson 4.1, which is all about congruence. Specifically, I think they're in this section, they're talking about triangle congruence, but I think they're just kind of keeping it general with any shape of congruence for 4.1. So congruence is just a fancy word for something that's equal, something that's the same, right? So if you say that, these two shapes right here are congruent, what you're basically saying is that I can cut each of these shapes out of this page, lay them on top of each other, and they're going to be the exact same shape. They're going to be the same lengths for the sides, the same angles. So congruence means that these two things, if they are congruent, means they're perfectly identical to each other. They're scans, they're mirror images of each other, okay? So let's go ahead and take a look at example 1. Example 1, what is the relationship between rigid motions and congruence? So this is just kind of I'm sorry, I just read the essential question. Example 1, understanding congruence. Suppose there's a rigid motion that maps one figure to another. Remember rigid motions, that's a definition we've covered in the past. If you forgot what that means, just go back and look at that. Rigid motion is basically doing something to a shape, to whatever you're dealing with, and it doesn't change the angles in that shape, and it doesn't change the size. So if I have, like a triangle here, obviously this is going to be perfectly equal because I'm hand drawing them. If I take this triangle, we'll call that the pre-image, and I say that this is the image, right? Well, those two things, that whatever happened here, whatever this thing that happened from here to here, from the pre-image to the image, wasn't a rigid motion because this triangle is bigger than this triangle. Same thing as if I said from that triangle and I produced that triangle, right? That is not a rigid motion because the size changed, it became smaller. But as long as I take a triangle or I take any shape, I do some motions, I do something to it, and it produces the exact same triangle, right? Imagine that those two things are exactly the same. That is a rigid motion. So things like reflections, things like translations, where I take a triangle and I kind of move it around the page, those are rigid motions. I just can't change the size of the item, and it can't change the angles within the item. Why does that show that the two figures are congruent? So let me reread this. Suppose that there's a rigid motion that maps one figure to another. Why does that show that the two figures are congruent? So here they're basically taking this pre-image right here. That's what they're starting with, is this black shape, whatever that is. And then it looks like they are reflecting it across that line, x equals -1. You could see it, that dotted line right there. They're reflecting it, and then they're translating it. Looks like they're moving it down and right, or right and down. So starting with this pre-image, what they're doing here is just measuring the sides. So for example, if you go from E to F, the side EF looks like it's 2 boxes long. So for EF, they have 2, right? A to F looks like it's 3 boxes long. So A to F or F to A is 3. So what they're doing is they're doing these transformations. They're reflecting it and translating it down and right. And they're showing that if you measure the sides of this shape, after you reflect it and translate it, the sides are the exact same length. Nothing changed shapes. So that side BC that started off as 1 unit, that's the new side right there. After they reflect it and translate it, it's still 1 unit long, right? EF was 2 units. After you reflect it and translate it, KL is the new EF, right? But it's still 2 units long. So what they're saying, what they're trying to prove to you with example 1 is you can do a reflection, you can do a translation, you could move this thing around the page, but it doesn't change the shape of the item, of the figure, okay? As long as it doesn't change the shape, it doesn't change the angles, it just doesn't change the size of the shape, it's not like it got bigger, then it's a rigid motion, okay? I think I got a little bit of a definition here, a concept, the idea of congruence. Again, congruence is just a fancy word for something being equal, a copy. So figures that have the same size and shape are said to be congruent. Two figures are congruent if there is a rigid motion that maps one figure onto the other. So in this shape, the pre-image is the black triangle, the image is the red. What they're showing you is that I take that pre-image, I reflect it across line M. It's the same exact shape, okay? So they have to be congruent. A rigid motion is sometimes called a congruence transformation because it maps a figure to a congruent figure. So if I do a reflection, if I do a translation, you automatically know that that pre-image and image have to be congruent to each other, because as long as you did a rigid motion, the size and the angles will not change. It'll be the exact same shape. All right. Example 2, verify congruence. Given triangle XYZ is congruent, that's like an icon, right? That's a symbol that shows congruence. It's an equal sign with kind of a little squiggly line above it. That means congruent. To triangle ABC, what composition of rigid motions maps XYZ to ABC? So you want to go from XYZ to ABC. So XYZ is right here, ABC is right here. This is one of those ideas, and I think the reason why I always struggled with geometry when I did this in class or when I was a kid, right, was because I was really solid with algebra. I could put down equations and I can do the steps and do what I'm supposed to do and get to the answer. But some of this kind of stuff really takes some imagination, which is kind of embarrassing to say, but I just don't have a huge imagination, right? It's really hard for me to kind of imagine this triangle coming off the page and flipping around or turning or reflecting or sliding around. That's something that I struggled with as a kid. I've gotten better at it now that I've practiced it more, but if you're struggling with that, that's okay. Don't feel like you're alone. Just keep working on it. So if I'm trying to go from this pre-image to this image here, it looks like the first thing I'd want to do is reflect that pre-image. If I reflect it across a line, it's going to reflect over to the other side. But if I reflect this triangle, imagine reflecting it across the line like 0.5, right? Right here in the middle. Imagine reflecting it across that line. It's not going to be the same exact image. So I think what they're wanting you to do is focus on rotating this image. Imagine I can take this triangle and I can spin it, right? Imagine there was a nail through point Z. Like I pounded a nail through there and I just spun it around. Okay, I spun it around. If I pounded a nail through point Z and I spun this triangle around 180 degrees, it would look exactly like the image, right? Again, imagine pounding a nail through point Z, taking that triangle off the page and spinning it 180 degrees. It would look just like that triangle. It wouldn't be in the same place, right? Point Z would still be at point Z because I'm rotating it around that point. So I'd have to shift it left, right, up, and down, but at least the orientation of the pre-image would be correct. So putting a pin through point Z, rotating it around 180 degrees, right? So starting off with that triangle, rotating it around 180 degrees, it would look exactly like this triangle here. But what I'd have is this triangle rotated 180 degrees, but it would be still pointed right here, right? It would be there to there to there to there. So what I'd have to do is I'd have to take that image and shift it to the right a couple spaces. So I think what they're getting at here, remember the way you read these transformations here is you always start with the one on the right and then you perform the one on the left. So this is saying little r, rotate it 180 degrees around point Z. So put a pin in point Z, rotate that triangle 180 degrees around, and then transform it, translate it 3 units to the right, 0 units up or down. Remember these numbers inside the parentheses. The first number means left or right. The second number means up or down. So I know it's 3 units to the right because it's a positive 3. So if I can imagine this, I take this triangle, rotate it 180 degrees, so that way it kind of flips over to the right, and then I shift the whole thing 3 units to the right, I'll have the exact same figure. And they are congruent, right? They have to be congruent. If I reflect, if I rotate, if I translate, they have to be congruent to each other. They have to be equal. Example 3, identify congruent figures. So given ABC, EFG, and JKL, which triangles are congruent? The big idea here is to try to pick a side and see if the sides will correlate to another triangle. So for example, if I look at ABC and EFG, ignore this one down here right now, but if I look at these two, do the side lengths look the same? Well, I'm kind of assuming that these weren't rotated, right? It kind of looks like this orientation is just about the same as this orientation. So what I'm trying to say is that BC should map, if they're congruent, to FG. Those two are the same side, or that's what we're trying to show, that they're the same side. So let's look and see. It looks like to get to BC, you have to go up 1/3. So if I'm going from FG, as long as I go up 1/3, I'll have, well, at least one of the sides are congruent, right? So from BC, I have to go up 1/3. To go FG, I have to go up 2/3. No, those two are not equivalent to each other. They're not congruent. If I have another triangle like this one down here, JKL, let's check that. It looks like I go from ABC to JKL. It looks like I have to do some things. I might have to rotate it. I might have to reflect it. I might have to translate it left, right, up, and down. That doesn't matter. You're just trying to check to see if these sides are all congruent. Well, like I said, if I'm looking at these two triangles, to me, it looks like, and I'll go ahead and write this down. It looks like BC will map to KL, right? This side here, BC, hopefully we're gonna see if it maps to KL. And then AB will map to JK, which means AC, hopefully, again, we're gonna see if this is a congruent triangle. AC will map to JL. All right, let's look. So to go from B to C, I have to go up 1/3. So for KL, let's look, up 1/3. So that's good so far, right? That's congruent, they're the same. What about AB? I have to go up 1, 2, 3, 4/1. So as long as I go up 4/1, I'm good to go. Let's look, up 1, 2, 3, 4/1, cool. So those two are congruent. Now let's look at AC and JL. So AC, it looks like I have to go over 1, 2, 3, 4, up 1, 2, 3, 4, 5. So over 4, up 5. Let's look here. 1, 2, 3, 4, 1, 2, 3, 4, 5. Perfect. So all of those sides that corresponded, or they map up to from the pre-image to the image, all of those distances are the same. Up 1/4, up 3/5, whatever the distance is. As long as they all map to each other, then we know that those two triangles, ABC and JKL, have to be congruent to each other. Okay? We know that ABC is not congruent to EFG because the sides aren't the same distance, right? BC should correspond to FG. You can just look at that and kind of tell. From B to C, it's up 1/3. From F to G, it's up 2/3. It's not the same thing. Is that example 3? Yeah, wow, going quick. Okay, example 4. Determine congruence. Let's see if I can focus this a little bit. Which pairs of objects are congruent? If a pair of objects are congruent, I think it should say, is congruent, describe a composition of rigid motions that maps one to the other. So like I said, there are some motions like reflections, like translations, that will take a pre-image, map it to an image, and they'll be congruent. The size won't change, the angles won't change, stuff like that. So which pairs of objects are congruent? Well, it looks like if you look at these two figures, it looks like if I reflect this, and I'll just use my pen as my line, if I drew a line perfectly down the middle of those two things, right down the middle right there, and I reflect it across that line, it looks like that image would map to that image. So I would say, yes, these two are congruent. I can reflect them across this imaginary line right here, and then they'll be the same exact shape. Okay. Just looking at these two picture frames, right? I guess that's what they are. These are definitely not congruent, right? You can see that the thickness of, this top frame right here is a lot thicker than this top frame right here. You could see that this side is a lot longer than this side. So again, for something to be congruent, they cannot change sizes. It can't get bigger, it can't get smaller, it can't get longer. And you can't change the angle of that shape. So if this is a right angle, then this has to be a right angle, okay? Just based off of that picture, the sides being different lengths, the thickness of each side being different lengths, these things are not congruent. What about these puzzles? So looking at that, ooh, this one's gonna be a little bit more tricky. I wish you could kind of actually have this like a tangible puzzle to kind of play with. It looks like if I rotate this image, if I take that image and rotate it 90 degrees, so if it's like this and I just rotate it 90 degrees on its side, rotate that 90 degrees and then reflect it, I'll have the exact same image. Okay, so let me walk you through that again. So going from this image to this image, if I take this image and I rotate it 90 degrees, so this red bar that's across the top is now up the side, I have that rotated 90 degrees, then I can just reflect it across this imaginary line right in the middle. And then I reflect that across that line and I'll have the exact same shape. So I say, yes, those puzzles are congruent. Apply congruence. A boat builder plans to connect two pieces of wood by using a puzzle joint as shown. For a successful joint, each unit must be congruent. Okay. Given unit A, what composition of rigid motions maps unit A onto unit B? So this is a little bit confusing, but just kind of ignore these parts, like this part up top and this part down the side. You're just looking at this puzzle piece A right here. If I wanted to map puzzle piece A and see if it's congruent to puzzle piece B, all you'd have to do is translate it down, right? You just have to move it down and then it would map, it would lie right on top of B. And then on page 154, you've got a concept summary. Again, the big idea from this section with congruence is you have to have rigid motions. If you forgot what rigid motions are, go back in your notes. We've talked about it a bunch of times. But rigid motions are basically things that you can do to a shape that doesn't change the size of the shape, doesn't make it bigger or smaller, and it doesn't change the angles within that shape. So I can't start off with something like this and then end up with something like this, right? Not only did the size change, but the angles changed. That's a big no-no. So that is not a rigid motion there. It has to be the same exact thing that you're dealing with. You're just basically moving it around the page. You can reflect it, you can translate it, you can rotate it, you can do things like that. All right. Next, we'll take a look at the practice problems on page 155, 14 through 17. So for number 14, given the reflection of M, so you're going to reflect across line M, that's what that means, reflection across line M of triangle PQR equals its image, triangle P prime, Q prime, R prime. So that's how you read that. Reflect, it's a capital R, so that's reflect. Lowercase r is rotate. We saw that in an example earlier. Across line M, triangle PQR, it'll give you triangle P prime, Q prime, R prime. So from the pre-image to the image. Does the image and the pre-image have equal perimeters? So that's kind of the distance around that shape. What do you think? Well, like we talked about, I can take a shape, I can rotate it, I can reflect it, I can translate it, which means move it left, right, move it up or down, and it'll be a rigid motion. It won't change the size of that shape. So if I measure the distance around that pre-image and all I do is reflect it across line M, then the distance around this image has to be exactly the same. I didn't change the size of that shape. If I reflect something, it doesn't change the size, it doesn't change the actual shape. All it does is give you a mirror image of the original shape that you started with. So would these two things, would this pre-image and this image have the same perimeter measurements? Absolutely. A reflection will give you a mirror image, a carbon copy of that shape. So yes. Number 15, given WXYZ is congruent to WTUV, so they're telling you that they are congruent. Remember that symbol right there means congruency. It means they're equal, it's the same shape. Describe a composition of rigid motions that maps WXYZ to WTUV. The order here matters. Let me get a piece of paper. So when they tell you WXYZ, describe a composition of rigid motion, so describe those transformations that maps WXYZ to WTUV, okay? What they're saying here is that these things, these points will go in the same order. W will map to W, the next point X will map to the next point T, the next point Y will map to the next point U, the final point Z will map to the final point V. So the order does matter. You know, if they're going clockwise and they say like this, W, X, Y, and Z, if those are the original points, well then after I do some transformations here, it has to be W, T, U, and V. Okay, so Z has to map to V, Y has to map to U, X has to map to T, and obviously W is itself, right? So let's check and see. The first thing I'm thinking is that based off of these notes that I just wrote, I want V and Z to land on top of each other. I want U and Y to land on top of each other. So U and Y, V and Z, T and X, those all have to map. And I think what I do is if I pound a nail through W, right? Imagine literally like putting a pin through W, taking that pre-image and rotating, this is my pre-image. Well, I guess it doesn't matter. You can do either one. We'll talk about this bottom one being my pre-image and this being my image. If I put a pin through W and I take that pre-image down here at the bottom and I rotate it 90 degrees counterclockwise, it'll be the exact same shape. Okay. Again, this takes some imagination. So imagine putting a pin through W, cutting this bottom triangle out and rotating it around point W, rotating it up on top of this triangle up here. X would lay right on top of T, Y would lay right on top of U, Z would lay right on top of V. So describe a composition of rigid motions. Well, one of them would be rotate 90 degrees counterclockwise. I think that's the one that I would stick with. Rotate 90 degrees counterclockwise. I'm not seeing any right off the bat, like if I can do multiple rigid motions, that's the only one I'm seeing right now. So if there is another one, let me know if you have any questions about that and I'll verify that it works. But the only one I'm thinking of is just rotating that 90 degrees counterclockwise. 16, are A, B, C, D, and E, F, G, H congruent? So this goes back to us talking about the distances of those sides, okay? Just by looking at these two images, there's not really a pre-image or an image. You can refer to them as that, but it doesn't matter. It looks like BC, hopefully, will be the same side as GF, right? HE should map to AD. I don't really care how they map to each other. I'm just verifying that the distances are the same, right? So let's check and see. BC looks like it's up 1 over 1. GF looks like it's up 1 over 1. Perfect. So one of the four sides, good to go. HE looks like it's up 2 over 2. AD looks like it's up 2 over 2. So it looks like HE and AD are the same length. Let's check BA. So it looks like it's up 1, 2, 3, 4 over 1, right? Up 4 over 1. So FE would be the same side that maps to AB. So up 1, 2, 3, 4 over 1. So that's good. And then our final side, CD looks like it should map to HG. So up 1, 2, 3 over 2. Up 1, 2, 3 over 2. So what I did was I kind of paired up the sides. I said that BC was paired up with FG or GF, doesn't matter what you call it. And I verified that they were the same up and overs, up 1 over 1, up 1 over 1. I said that AD was paired up with HE and they go up 2 over 2, up 2 over 2. So the first step here is to kind of pair up which sides go with which sides and then verify that you're going up and over the same amount. In this case, I would say yes. It must have been, they must be a composition of rigid motions because they are identical shapes. They are congruent. So if so, describe a composition of rigid motions that maps ABCD to EFGH. So how can I get from this quadrilateral to this quadrilateral? Well, the first thing I'm thinking of is that I can rotate this thing. I'm trying to think, how can I go from this shape to this shape here? I would say maybe let's go ahead and reflect this across the y-axis. So I take all 4 of these points and I reflect it across the y-axis. So I take that quadrilateral and I flip it over the y-axis. So again, this takes a little bit of imagination, right? I don't really want to draw in my book, but I probably should. So D prime is going to be right there. C looks like it's 1, 2, 3 units away. So C prime would be 1, 2, 3 units away, right? So take all of those pre-image points and reflect them across the y-axis. And then I think if you take that image and you reflect it across the x-axis, it's going to be the same thing. That's what I'm seeing. So if you want to, you're more than welcome to go to Desmos and type this in, and you can plot these points and reflect them across the y-axis and then the x-axis. But I'm pretty sure you're going to get the same exact shape. So let me just kind of sketch this out real quick. So if I start with something like, something like that, right? I mean, obviously it's not perfect, but you get the idea. And then I reflect it across the y-axis. That's that one right there. So if I reflect it across the y-axis, I'll get something like, let's see if I don't screw this up. So we'll call that A, B, C, D. So this is A prime, D prime, B prime, C prime, okay? So I just reflected it across that y-axis. And now what I'm gonna do is take that image and I'm gonna reflect it across the x-axis. So A prime would come down here, A double prime, I mean. D double prime would stay right there. B double prime would come up there, and C double prime would maybe come up here. Of course, I am like just totally sketching this, right? So it's not perfect, but I think that's the way, that's what I'm talking about. So take that pre-image, reflect it across the y-axis, take that image that I just reflected across the y-axis and reflect it across the x-axis, and I think you'd have a congruent shape. 17. Which objects are congruent? For any congruent objects, describe a composition of rigid motions that maps the pre-image to the image. Well, I mean, there's one that's definitely not congruent, right? B is not congruent to any of these shapes here because B is way larger than A or C. So right off the bat, B is garbage. That is not congruent to anything. A and C, though, those look like they're the same size. They look like they're the same shape, but I think the only difference is that they're mirror images of each other. So if I take A and I reflect it, right? I take A and I flip it over, I think you'll have the same shape as C. So B is not congruent to anything. A and C are congruent. They're the same size and they are the same shape. All you have to do is take that shape A and reflect it and you'll get shape C.